if you're going to write your own programs for the Sinclair Spectrum, then there are various things you'll need to know. Now, obviously, you'll have to decide what sort of programs you want to write. Games or educational programs, perhaps. You'll also need to know what the machine is capable of. Colors, text, graphics, calculations. And you'll also need to know a certain amount about the basic language, which is the way that you'll be giving your instructions to the machine. Now, if you've been through the Horizons cassette that came with the machine, then you'll have seen some examples of what it can do. You'll have seen examples of text and of graphics, colors and of sound. So what we're going to do during this videotape is discuss the basic language, the different statements that you're going to be using in order to get the machine to do what you want it to. Now, we won't have time to tell you everything about every statement, so you're going to depend quite heavily on the instruction book that came with the machine. We'll be able to discuss certain of the statements and give you ideas as to how to use them, but we'll always rely on you to go back to the manual to check out the details and learn those statements thoroughly. So, before we start looking at the basic language, let's take a quick look at the hardware that you're going to be using, the different parts of your computer system. Now, you'll spend most of your time looking at the screen, and so we should look at the different parts that there are in front of you. Around the edge, we have the border, which in fact is in two parts, because these two lines, which are invisible at the moment, are known as the input area. And any information that you type into the computer will go in and appear on the screen in this position. And this input area is also used by the computer to send you certain messages. Now, the part that I have colored blue here is the paper. And that's the main part of the screen for displaying information. And on the paper, the information that is displayed in ink. So when we talk about the color of the paper, or the color of the border, or the color of the ink, we're always talking about these parts of the information on the screen. Now, you'll be depending upon your cassette recorder player for copying programs into the computer and saving the programs that you write, and also perhaps saving data, information that will be used by those programs. Now, I'm using a special cassette player that's designed to be used with computers, but you may find that one you have already will work quite well. And if you've been through the Horizon tape, then you will know about setting the volume level so that it works correctly with your computer. Now, your main communication with the computer is going to be through the keyboard. And at first sight, it may look a little daunting, because every key on the keyboard seems to have 5 or 6 different meanings, depending on whether you read red or green or white. But it's really quite straightforward as long as you approach it carefully. Let's look at one specific key and look at the legends that are written on that key. Now, the B key has the word border underneath it. Above it, the word bin, below it, the word bright, and also printed in red on the key itself is a star. Now, at different times, that key can produce any of those effects. In order to know which one it'll produce when you press it, we need to look at the cursor that you see at the bottom of the screen. The flashing K cursor tells us that BASIC is expecting a keyword. The keyword that's written on the B key is the word border. And if we press the B key when our cursor is flashing K, we'll get the word border. Notice that now our cursor has changed. It's no longer a flashing K, but a flashing L. This means that BASIC is no longer expecting us to type a keyword, but is expecting a letter or a number. If we press the B key again, we get a small b. We get the letter that is printed on the key. Now that is the start of a basic instruction. It's a border instruction. In fact, it's not valid, and if we press Enter now, we'll see what BASIC does when we try to give it an invalid instruction. There's the Enter key. We get a message, variable not found. For the moment, we'll ignore that message. We'll press Enter again, which will give us our K back again. Well, let's put in a valid border instruction and see how it works. Pressing B again gives us border, and this time we're going to follow it with a number, because you'll see that the numbers at the top of the keyboard have colors written above them. Let's try a green border. Green is above the 4 key, so if we say border 4 and then press Enter again, we have an immediate result. The border has gone green. If we didn't like green, we could use another border instruction, border white or 7. Pressing Enter immediately returns us to our white border. Well, that's all very well for instructions that we want obeyed immediately. But if we want to put a program into the computer, then we don't want the instructions obeyed immediately. We want the computer to remember them all, so that they can all be obeyed together a little later. And if we look at the program I've put into the computer now, you'll see how we achieve this. Now here's a part of a basic program, and you'll see it's a mixture of numbers and letters. Now each of these, rem, paper, ink, CLS, is a keyword in the basic language. And they're easy to spot in this listing because they're all in uppercase. But all these small letters that you see are words that I've typed in using the keyboard. But the important thing to note is that at the beginning of each of these lines is a number, and it's called a line number. And it's because of these line numbers that BASIC knows that each of these lines is not an instruction to be executed immediately, but it's a line that's to be stored in a program. Now it doesn't matter, as in this case, that our statement in BASIC has got so long it's gone on to the next line. That's still considered to be one line of BASIC. So every line in our program has a number. Most of them go up 10 at a time. But here we've got 1 and 2 at the beginning. And BASIC uses these numbers to work out in what order we're going to put statements into the program. We'll put a border statement between this one, setting the paper, and this one, setting the ink. So we need to give it a number between 10 and 20. Let's give it number 15. We type 1 and 5, because our number keys don't have keywords on, so we get 15. Let's press the B key. We still have a flashing K cursor, and so we get border. Let's ask for a green border, and green was above the number 4. Now when we press Enter, the border hasn't changed color. That instruction hasn't been obeyed. But if we look back to the list of instructions, we now have number 15, border 4. So that new line of BASIC, that new statement, has been put into our program, and the place it's been put has been controlled by the number we gave it, its line number. 15 comes between 10 and 20, and so border was put between paper and ink. Now that border statement will only be executed if we run the program. How do we run the program? Well, the R key has the word run on it. If I press the R key now, you'll see that BASIC gives me the word run. This is going to tell BASIC to execute all those statements in the program. It won't do it until we press enter. So let's press enter now. The program has started to run, and our border statement asking for a green border has given it this effect. Now we won't look at the rest of that program for the moment, because we'll be coming back to it a little later. But what we will do is look at some of the basic statements that are within that program. Now if we look at the text we can see on the screen, then the numbers we can type simply by using the number keys. These small letters we can type by using the letter keys. And some of these words that are in capital letters we can get with a single press of a key. But some of them, paper, ink, inverse, aren't printed in white on the key. They're printed in different colors around the key. And also these punctuation marks, a comma, a semicolon, a quotation mark. Now they're on the same keys as letters, but they're not printed in white. So we'll need to go back to the keyboard to see how we can get these alternative meanings out of the keys on the keyboard. Now down towards the bottom right of the keyboard, you'll see symbol shift. And because the words are printed in red on the key, that tells us that symbol shift is used to get these red symbols that are printed on the other keys, equals, plus, minus, and all the others. But that symbol shift key has to be held down while we press the other key. Let's see the effect of using the L key. By itself, with a K cursor, that gives us let. With an L cursor, pressing the same key again, gives us a small letter L. But if we hold down the symbol shift key while we press L, we get the red symbol that's printed on that key, the equal sign. So we'll use symbol shift held down in conjunction with another key to get any of the red symbols, or in some case words, that are printed on the keys. That still leaves us the problem of how to get the green letters, which are printed above the keys, and the red ones, which are printed below. And in order to achieve that, we have to go into what's called extended mode. You've seen the symbol shift used here, and this time we're going to use it in conjunction with the caps shift key, which you see at the left of the keyboard. If you watch the flashing K cursor, if I press both of these together, it changes to an E, meaning extended mode. And now, if I press a key, the meaning of the key is the meaning printed in green above the key. If I press the C key, which has L print in green above it, we get L print on the screen. Notice that the cursor has changed back to a flashing L. So extended mode will only work for that single key depression. Let's go into extended mode again. But this time, while I press the C key, I'm going to hold down the symbol shift. Now you see that the word paper has appeared. And that's the word that's printed in red underneath the C key. So we can obtain the green and red printing above and below the keys by going into extended mode, pressing symbol shift and caps shift at the same time. Then if we press a key, we'll get the green meaning above it. But if we hold down the symbol shift, we get the red meaning below it. Now we've seen how we can type some of those statements using the keyboard. Let's take a look to see how they're used inside the program and what they do. The first two statements here are called REM, R-E-M, and that stands for a remark. Really, that's not part of the program at all, but it just allows us to put whatever we like as part of that statement as a remark about what the program does. It doesn't make any difference to the way the program executes or to the numbers it's going to print out, but it's a useful reminder as to which part of the program does which part of the calculation. Border we've seen, and that's used to set the color of the border. Paper and ink are used to set the color of the paper and ink respectively. They're each followed by a number, and those numbers will correspond to the colors printed above the number key. CLS is a nice simple statement. It stands for clear the screen. So as soon as we execute that statement, the whole of the paper area of the screen will be cleared and set to the paper color. So these three coloring statements and the one clear screen statement just set up the screen the way we want it for our program. A print statement doesn't print on paper, it prints on the screen. So this information, A, body, weight, will be printed in ink color 1 on paper that's color 5. That's ink blue on cyan or light blue paper. Another print statement here, and an input statement. Whereas the print statement prints information onto the screen, we'll see later that the input statement allows you to type information in through the keyboard. Now, a program will contain many statements. We can see a few of them at the beginning of the screen here. But what if we wanted to look at all the statements in the program? Well, there's a special command we'll use called a list command, which will allow us to see all the statements in the program, not just one screenful at a time. And the list command is on the K key. If I press K now, I have list. If I press enter, well, we start with the same information that we had before. A listing of the statements in the program from the beginning downwards. But at the bottom of the screen, we have this message, scroll, ? And the computer does this to tell us that it has more information to show us, but it can't get it onto the screen. If it tried to show us the whole program on the screen, then the lines would be lost from the top. Yes, we want to scroll. We want to see more of the program. If we press the Enter key, you can see the lines of program run up the screen so that we can see the next screenful. Again, the same message, scroll. So each time we press Enter, we'll get another screenful of the program. We now don't have the message scroll. We have a message saying OK. And that tells us that that's the last line of the program. So we can use a list command to run through and see all the statements in the program. Let's do it again. List, enter. Only this time, we don't want to see any more. Instead of pressing the enter key in response to the question scroll, we press the break key. That says stop scrolling. Don't show me anymore. So we've seen how to put lines into a basic program by typing a line number and then the basic statement. And we've seen how we can use the keyboard to obtain all the words and characters that we're going to need. So before I show you a complete program, the one other subject I'd like to look at is the subject of editing, so that if we do make a mistake when we've typed in a line in our program, then we don't have to type the complete line again. We can just make a change to the line in the program. And we'll use the same program and make some changes to it. Now, beside line 15, you see a little arrowhead. And that tells us that the computer thinks this is the current line. But if we're going to make some changes, we'll do it on this line. Now we can make that arrowhead point to different lines by using the up and down arrows on the keyboard. Now they're above the 6 and 7 keys, but they're printed in white, so they behave like capital letters. In order to get up and down, we have to use the caps shift key at the same time. Now I'll hold down caps shift and press 7, which is the up arrow key. You can see the little arrowhead has moved up to line 10. Press it again, it's gone to line 2, and again to line 1. If I try to go up any further, I can't. I'm at the beginning of the program. I'm still holding down the caps shift key, but now, as I press the 6 key, you can see the arrowhead move down the screen, one numbered line at a time. I'm now on the bottom line, which is line 140. If I go down again, and the text on the screen moves up a little bit, so that the next line, 150, comes into view. And I can carry on going down. Each time, the arrowhead moves down one line. So that allows us to get to any particular line, but slowly sometimes. If we want to make a big jump from one part of our program to another, we can use the list command again. List, only this time I'm going to put a number after it. If I say list 10, list 10, and press enter, you can see that my program has been listed starting from line 10, and that little arrowhead is now pointing to line 10. Because there's more to be shown, I have this message scroll again. I'll press the break to say I don't want to scroll. Now let's suppose we want to change this line 10. Instead of saying paper 5, we want to say paper 7. I could just type the line in again, 10, paper 7. But you'll see above the number 1 key the word edit. Again, it's printed in white, so if I hold down caps shift and press edit, then we have a copy of line 10 transferred from the current line down to this input area. And there's a cursor in the middle of it. The line is still in our program, but now we have a copy of the line that we can make changes to. Again, we use the arrows from the keyboard, but this time we want the left and right arrows, which you see above the 5 key and the 7 key. Printed in white, so we must hold down the caps shift. But if I hold caps shift and press 8, my flashing cursor has moved from in front of paper to following paper. Press it again, and it goes past the 5. Pressing the left arrow key, still holding down caps shift, I move back towards the left. So by using 5 and 8, which are my left and right arrow keys, I can go to any part of the line that I want to. Now I wanted to change 5 to 7. To do that, I have to delete the 5 and then type in a 7. And you'll see that above the 0 key is the word delete, printed in white. So if I hold down the cap shift and delete by pressing the 0 key, the 5's gone. My line now just says 10 paper. I can type in 7, and now I have line 10, paper 7. What I need to do now is to take this line and put it into my program, replacing that one. All I have to do is press Enter. You can see the result. Line 10 is still the current line. I have my little arrowhead there. But now the new version of the line, paper 7, is in my listing. The old one, the one that said paper 5, has gone completely. To show that this really worked, that my program has been changed, let me run it again. Pressing R for run, followed by Enter. The program comes again, but this time the paper is white, which is color 7. We've now recorded onto the soundtrack of this video cassette a computer program which you can copy onto an audio cassette and put into your own computer. And this will give you some practice at using the editing and keyboard facilities that we've been discussing. And after you've played with that program and had some practice, then we'll come back and look at the writing of a complete basic program. Well, let's run this program, see what it does, and then see how it does it. Well, the first thing we see is that information is printed at the top of the screen. The first two lines are in dark blue on light blue, and the third line is printed with the colors reversed, light blue letters on a dark blue background. Now down here, in the input area, we've got 3 lines of printing. Because I've asked for several things to be printed down here, this input area has got bigger. It's moved up the screen a little bit. And we're being asked to press M if we're male, F if we're female, and then to press the Enter key. A flashing cursor here, between quotation marks, tells us that we're expected to type in some characters of some kind. Well, let me type an M, and you can see the M appear, and now I'll press Enter. The result of that is another line has appeared at the top here, saying, I'm male, and we are being asked another question down here. Now this time we're being asked for a number. Type your height in centimeters. Notice we have no quotation marks around the flashing cursor now. This tells us that a number is expected. Well, let's put 200 as my height in centimeters and press Enter again. The information has been repeated up here, so the number we typed in has been put up in this part of the screen, and we have another question. Am I slightly built, S, medium build, M, or heavy build, H? Well, let's put M for medium. Press Enter. 2 more lines on the screen. Again, medium is as a result of what I typed in. The 80 is the result of the calculation. The program has calculated what it thinks I should weigh. And notice that that 80 is flashing. At the bottom here, we've got a message saying OK, with a number in front saying 0. This tells us that our program has finished, and finished correctly. 440 is the number of the line in the program where we finished. So the program has taken in 3 pieces of information. We typed M for male, 200 for the height, and M again for medium build. As a result of those 3 pieces of information, the program has done a calculation and has come up with a number 80. All the rest of the information you see on the screen, the whole of the first 3 lines, and most of these 4 lines, is constant information. It'll be the same every time the program is run. Well, that's what the program does. Let's now take a look at the statements we used to do that. If we list the program, we can analyze the statements we used. Paper and ink we've seen used before, simply setting the paper and ink color. Clear the screen. So let's look at these 2 print statements, which printed the very first 2 lines of the heading. Print at 1,8. The print statement says put information onto the screen. If I follow it with at 1,8, I mean position 8 on line 1. Line 0 is at the top, so the second line is line 1. Position 8 is about there. So a body weight, which I put inside quotation marks, will be printed along that part of the screen. Anytime that we want to print fixed information, information that's never going to change, we can simply put quotation mark there and a quotation mark there. Whatever we put between those quotation marks will be printed. In the same way, the next print statement prints at line 2, position 9. So line 2, position 9, the word calculator. Now this print statement printed out don't believe the figures. But they were printed out in reverse printing. Instead of dark blue writing on pale blue paper, it was the other way around. And that's because of this line. Line 60 says inverse 1. Now, after I've written that statement, any print statements that occur will be printed in inverse printing. So instead of ink color printed onto paper color, it'll be the other way around. Paper color printed onto ink color. Line 80 changes it back again. So we've only got 1 print statement being used to show us inverse printing. Now, the first thing the program did was to input a value. Let's look at this input statement. Input says we want whoever is using the program to type a value on the keyboard, and we want that value to be put into the program. I put input and then followed by quotation marks all this information, because you can't ask somebody to type something in unless you tell them what it is you want typed. So this information was all printed in the input area before we were ready to type our information in. But after all that, after then press enter, I put a semicolon, an A, and a $. Now the $A is not something that's to be printed. There are no quotation marks around it. $A is the name of a variable. We said something's going to be typed in on the keyboard and it's going to be put into the computer. Put it in part of the memory and call it $A. The $sign means it's going to be just a string of characters. It's not going to be a number. So we're not going to do any calculations with this. If you remember, the first thing we typed in was an M for male and an F for female. Just a single letter followed by enter. A single letter followed by a $sign is the name of a piece of storage where we can hold a string of characters, for example, one letter. Now later in the program we're going to use $, again, because we'll want to see what character we typed on the keyboard. This happens in the next line. If $, is equal to M. Now here we're asking a question about that character that was typed in. We're saying, is the value that's in the variable $, an M? If asks a question, and it will only do something if that gives us a true answer, a yes. So if we typed M in response to this input statement, then the if here will give a yes. Is $, equal to M? Yes, it is. We did type an M. The next statement, if $, is equal to F, asks another question about the same variable. Was it an F that we typed in? M and F were the two values that were expected by the program. $, in the same way, is another variable. Because it's got a $, after its name, it's going to be something that's going to hold characters. Whereas with $, we put a value in there by typing it in an input statement. A let statement allows us to put whatever value we like into that variable. I've said put M-A-L-E, the word male, into the string variable $. Quotation mark there and another quotation mark there means that this is a constant value. So this let statement will always put the four characters M-A-L-E into $. So if we've got $, having a value of M, then $, will get the value male. Similarly, if $, is an F, if we typed an F in response to this input statement, then $, will get the value female. Remember, just because a line wraps round one end of the screen and appears again at the left-hand side, it doesn't matter. It's all one line. Up here we have another let statement. Now what did we put into $, here? We put nothing. Quotation mark, quotation mark. We said, put into $, no characters at all. Why did we do that? Well, if we entered an M, then we put male into $. If we entered an F, we put female into $. But if we made a mistake and something different went into $, we don't get male or female put in there. $, will still have nothing in it. If $, has got nothing in it, that will be true. Then go to 100. So an if statement can make us jump to another part of the program. That means line 100. Where's line 100? There it is. We'll go round again. Let's run the program to see if that works. There's the first question. Press M or F. Well, suppose I press D. It's neither M nor F. When I enter that, I get the same question back again. The program knows it isn't an M, it isn't an F, and so it asks me the question again. Now, we won't go through all the individual statements that make up the rest of those questions and answers, because you'll be able to look at them yourself when you copy the program into your own computer. What we will do is look at the end of the program, where we do the calculation of the body weight and we print the final answer. These are the last 5 lines of the program. Line 400 is another let statement. It's going to do a calculation here and put the result of the calculation into my variable called W. Now, h is the height in centimeters, and we set that by inputting h. I'm multiplying it, and that asterisk is used for multiply, by 0.4. The next 3 lines, 410, 420, and 430, do further calculations depending on the other information we put in. If we put in F for female, then $S will be female, and what we do is take the value of W multiplied by 0.8 and put it back into W. So W becomes 4/5 of the value it had before. Similarly, if we're of heavy build, W equals W plus 6. We add 6 to W. And for slight build, we subtract 6 from W. So these 4 statements all put values into W. This an initial value, and then these 3 will change the value of W. And our final print statement, printing at 11.5, line 11, position 5, the words "you should weigh" W, that's the value we calculated, kilos. And around W, we've put flash 1 and flash 0, with semicolons separating the flash, the W, and the characters we wanted printed. Flash 1 says start flashing. So anything after this flash 1 in this print statement will be printed flashing. That's W, the weight. Flash 0 will switch it off again. So kilos will not be printed flashing. And in fact, we can emphasize text in another way by using bright instead of flash. Let's show the result of that final print statement using bright. There you see the result of replacing flash by bright. The number has been printed in a brighter form. And we can see the statement that did that by listing line 440, bright 1 and bright 0. Now we've looked at a lot of different statements in this program, and there are a lot of statements that we haven't had time to discuss in detail. So it's very important that you copy this program into your own computer and spend some time looking at it, seeing how we've used those statements, how we've assembled them together into a complete program. When we come back, we'll look at some more aspects of basic programming. Well, as you can see, the Sinclair Spectrum is quite capable of scribbling all over the screen. We're going to look at some of the statements that can be used to produce graphics on the screen. There are 3 main ones that we'll be looking at, and those are plot, draw, and circle. But before we look at the individual statements, let's take a look at the screen as it's used when we're using graphics. Now we have to think of the screen slightly differently when we're using graphics. Instead of thinking of this as being line 0, character 0, we have to think of the bottom left of the screen as being the point whose address is 0, 0. At any point on the screen, is identified with two numbers. One, its distance from the left-hand side, and the other, its distance up from the bottom. From position 0 at the left, we can go up to position 255 on the right. From position 0 at the bottom, we can go up to position 175 at the top. Let me give you some examples of those. So the point in this position is referred to by the numbers 128, 88. 128 across and 88 up. The point in this position here is 200 across from the left, 150 up from the bottom. So its two coordinates, the two numbers that identify it, are 200 and 150. The first two statements we'll look at are plot and draw. Now the plot statement takes us to a certain point on the screen and plots a single point at that position. And the draw statement, at least the simple one we'll look at first, will draw a straight line starting from that point. And we can see that in this very simple example. Here we have two lines that have been drawn on the screen. And if I list the program, which is only 3 statements, you'll see the 3 statements that did that. This is the point 100, 100. 100 from the left and 100 from the bottom. So line 10 moved to that point on the screen and drew a single dot. Now the draw statement started from that position and drew a straight line which was 10 in that direction and 10 in that direction. So we got a diagonal line. The second draw statement carries on from where the first one left off. It's going 10 in that direction again, but we've got minus 10 here. So it'll draw in a downward direction. And so we get a line that slopes like this. Now one nice thing about the difference between plot and draw is that we can use plot to take ourselves to any particular point on the screen, and then draw relative to that point. This means we can set up a series of draw statements to define a shape, and put that same shape in several different places on the screen by plotting to different points first before we execute the draw instructions. You see a very simple example of that here. Now these 4 draw statements will draw a square. The first one goes 10 to the right and 0 up or down. The second one doesn't go to left or right, but does 10 upwards, and so on for the other 2. If we run this very small program, we'll see the square, a small square in the bottom left-hand corner of the screen. But we can use those same 4 draw statements to put that square anywhere we like, by putting a plot statement in front of them, like this. So to get my square positioned here on the screen, I simply need to put in front of my 4 draw statements a plot that takes me to a suitable position. Plot 100, 100 takes me to this bottom left-hand corner, and then the 4 draw statements will go round the square. But suppose I wanted to draw several squares, or repeat the same shape several times on the screen. I don't want to repeat the same draw statements over and over again. And so this seems to be a good point to bring in the idea of a subroutine. And in the next piece of coding, you'll see what a subroutine is. So if we look at this coding, we see our 4 draw statements as before. After them, there's a new statement called return, and we'll see why that's there in just a moment. We have 3 plot statements, plot 100, 100, as we had before, plot 80, 20, and plot 0, 150. So these 3 plot statements will plot points at 3 different parts of the screen. And after each plot, I said go sub 1000. Now this go sub statement, together with this return statement, make this set of statements in our program into a subroutine. When BASIC reaches this go sub statement, it jumps to line 1000 and starts executing the statements there. When it reaches the return statement, it jumps back to the statement after the go sub. We execute this second plot and we go sub 1000 again. So once more we'll jump to this point, execute our draws and return, but this time we'll return to here. Another plot to move to yet another point on the screen and another go sub. So although we've only coded these 4 draw statements once in the program, they'll in fact be executed 3 times. Once after this plot, once after this plot, and once after this plot. And if I run the program, you'll see how it works. Very well. Our 3 plot statements have taken us to these 3 different points on the screen, and after each plot, we've drawn a square. So a subroutine is very useful if we have one piece of coding that needs to be repeated many times at different points in the program. Now, as you go on and write larger and more complicated programs, you'll find that this idea of subroutines becomes more and more useful, not only because you can repeat the same section of coding from different parts of the program, but also as an aid to breaking up the program into easily manageable parts. And you'll see, when you look at some more complicated programs, how they have been divided into subroutines. However, let's return to our draw statement and see how we can persuade it to do bent lines. Here's that same program again, but I've made one small change. I've added a 3rd number onto this draw statement, comma 3. Now if we put 3 numbers into a draw, the 3rd one is used by the computer to decide how much the line should curve as it goes the distance determined by the first 2 numbers. If we run this program again, we'll see the result of that. Each of our little squares now has a slightly bent top. And we can change the curvature, make it larger or smaller, by changing that 3rd number in the draw statement. Let's try something much bigger. Here I've changed the number to a 5. And if we run this again, we'll see the result. It's got to go through 5 radians, as they're called, of curvature to get from the beginning of the line to the end. And the bigger we make the number, the more it has to curve, up to a limit of just over 6, when we'd be getting a gigantic circular shape. See what's happened to this square. Although the first 2 lines were drawn successfully, as it curved round to do the 3rd line, it came off the paper into the border area. And at the bottom of the screen we have this message, integer out of range. And we'll always get this message if our drawing tries to go off the main part of the screen. But of course, if we want to draw complete circles, then we have a separate statement that'll do that for us. The circle statement. I drew 3 circles on the screen using 3 circle statements. The first 2 numbers in the circle statement are the coordinates of the center of the circle. So the first one and the 3rd one have both got a center at 100, 100. And so these are concentric circles. The 3rd item is the radius of the circle, the size of the circle. 20 for the inner one here, and 70 for the outer one, and 10 for the small one in the corner. So we can draw partial circles using draw. We can draw complete circles using a circle statement. So those are our basic graphic statements. Let's go back to that scribbling program you saw at the beginning and see how I wrote that. Now the scribbling looked random because within this coding we have the randomize statement and the RND function. which are the two facilities the spectrum gives us for putting random numbers into our program. If I run through this coding and show you how it works, you'll see what use I've made of those random numbers. I started with a plot statement, 128, 88, which is roughly in the middle of the screen. And I'm using the variables x and y to remember my current position. So I've set them to 128 and 88. Now YY and XX are being used to find a new point on the screen to draw to. And I've chosen random values for them somewhere on the screen. This draw statement calculates the distance I have to go horizontally and vertically to get from my first point here to the new point I've just worked out. And here I put into x the value of xx and into y the value of yy, so that I remember how far I've drawn to, because that's going to be my new starting point for the next draw. Here I go back to 50, think of a new random point to draw to it, and remember it in x and y. So as I go round and round this coding, I'll keep drawing lines to random points on the screen. Now the RND function gives us back a number between 0 and 1. It can be as small as 0, but it will never be quite as big as 1. So this value, RND times 170, is going to give us a number between 0 and 169. And that's the value we're putting into YY. RND multiplied by 250 will give us a random number, something between 0 and 249. And so that's the value that's going into XX. As we execute these statements over and over again, we'll get different values out of RND each time, which is why our line zigzagged across the screen. I put the randomized statement in at the beginning, which makes sure that each time we run the program, we'll get a different set of results. If I left out that randomize, I'd get the same values returned from RND each time the program was run. Randomize makes sure that they're different every time. Now we can use paper and ink with our graphic statements in the same way as we did with our text printing statements. But there is one thing that we do have to watch. In each character position on the screen, you can only have one ink color and one paper color at the same time. You'll see what I mean if you look at the screen now, where I've run the program again, but this time with color. It looks quite pretty at first sight, but if we look more closely, we'll see what's happened. This was a yellow line, and so the ink color in all these character positions was yellow. But we crossed it with a black line, and the black line was making all the ink colors black. So this little part of the yellow line that's sharing a character position with black has gone black itself. So we have to be very careful when we're designing colored graphics to keep our colors in separate character positions wherever possible. Now we haven't had time to cover the whole of BASIC in this videotape, but I hope we've covered enough to give you a good start along the road of writing your own programs. But it is most important that you look at the programs that we've given you, the ones we've recorded on the videotape, to see how we've constructed those programs and how we've used the different statements within them. And then when you've looked at the statements, check them yourself in the manual to make sure that you understand exactly how they work and how you can use them. And in later videotapes in this series, we'll carry on with learning BASIC. Hello. In this videotape, we're going to look at some of the further features that BASIC has to offer, some of the slightly more advanced ones. We'll be looking at three main areas. Firstly, we'll look at the facilities for holding larger amounts of data within your program than can be easily handled with single variables. And then we'll have a look at string manipulation, slicing strings of characters into smaller sections. And finally, we'll have a look at some animation, putting everything together into a complete game. But we'll start with the facilities for holding data. Let's run this program and see what it does. Well, it's inviting us to enter the name of a food. Let's start with something simple like beef. And it's come back to us telling us that beef is around 100 calories per ounce, and inviting us to enter another food. Let's try egg. Let's try fudge. Now, it's fairly obvious from looking at that output that this program contains a fair amount of data. We know it has the names of at least 3 different foodstuffs, and also their calorific values. So let's look to see how that information is being stored within the program. Well, lines 1000 onwards give us the clue as to how the information is stored. A whole series of statements, all called data statements. After each word data, we've put 2 values. The name of a food, which is a string of characters in quotation marks, and a number. And we've put a comma in between them. So in fact we have 16 values down here, 16 character values, and 16 numbers to go with them. So this is one way in which we can store raw data within a basic program. The question is, how can we get at that data? Well, we can see that by looking at the beginning of the program. Well, the first part of the program, before the data statements, is very short. We have an input statement, a read, an if, a print, and a goto. Well, the input statement simply invites us to enter a value, and that value is put into $, a string variable. Now, this read statement is new. What a read statement does is read values from data statements. So the very first time we execute this read, it's reading $, and C. So that's a string variable and a numeric variable. It'll take the first 2 data items, avocado and 25, and put them into those 2 variables. The if statement simply checks to see if $, is not equal to $. If they're not equal, it means that avocado is not the food we were looking for. It's not the value that was typed in there. And so we go back round to the read to execute it again. This time it'll read bacon and 130 into $, and C. And again, the test will be made. And we'll keep going round and round and round these 2 statements until this isn't true. When $, is equal to $, it means that somewhere down in this list we found the food that was asked for. If we'd entered carrot here, then we'd stop when we reached carrot at this point. A simple print statement to print out the name of the food and the value of its calorific content, this variable C that was read with the name of the food. And then a goto statement to repeat the complete process. Let's run it again, but this time let's make a mistake with the input. This time when I run the program, I'm going to put in a food that isn't in that list of data statements. I'm going to put in fish. I get nothing printed in the top of the screen, and I get this error message, out of data. And this message simply means that I've read and I've read and I've read through my list of data statements until I've got right to the bottom and there's no more data to read, and I've still tried to read again. Now, fairly obviously, this will happen if we type in a value that isn't anywhere in this list. This comparison will force us to go round and round, reading and reading, until we run out of data. So there's one problem, reading past the end of the list because the value we're looking for isn't there. But there are other possible problems. Just note that we do have beef in the list, and we do have corn in the list. Now let's try running the program using those two values. Let's start with corn. That's worked fine. Let's now try beef. And we've got the same message, out of data, which at first sight might seem to mean that we don't have beef in the list, but we know we have. Let's go back to the listing and we'll see why that happened. As soon as we find equal values here, we'll print out a message and we'll go back to the input statement. But we've read halfway down the list. Nothing is going to make us begin at the beginning of the list again. The first value we found was corn. So after we printed out the message about corn, BASIC is ready to read the next item in the list, which is cream. It's not automatically going to go back to look for beef. If we want it to start at the beginning of the list each time, then we must do that explicitly. And we do that with a restore statement. I'm going to add in this line, restore 1000, and it's going to be line 15. So it'll go in there to be executed as soon as we've entered a food. Now the effect of restore 1000 is to reset BASIC's pointer to that point in our list of data, so that the next read that BASIC executes will start at that point in the list. Now, for each new food I type in, BASIC will start to read from the beginning of the list again. Now, in fact, that's the only data I have in this program, and so I could have used restore without the 1000. In that case, BASIC would restore the pointer to the very first data statement in the complete program. So we can use data statements whenever there's a large fixed amount of information that we need to hold within the program. Although if we're going to process that information over and over again, as in that last example, then it's a little bit wasteful to reread it every time, going back to the beginning of the list and reading through every piece of information. So there's another facility for holding larger amounts of storage that we should look at perhaps in conjunction with it. And that's the idea of holding an array of information. Perhaps I can show you that with a small diagram. If we have a series of values, we could imagine them being held in a table. And we could give each item in the table a number. Here I've got 10 different values, and so I can call them values 1 through to 10. And so it becomes easier to talk about the third one, or number 7, or the 10th one, when I want to refer to a particular one of these values. And this is how we do it in BASIC. Now here's a slightly different version of the program we were looking at a moment ago. Let me point out the differences to you. There are 3 important differences. We have 3 dim statements in the program. And this stands for dimension. And it's the way in which we define one of these tables, one of these arrays. Let's look at line number 3 first. I said dimension, C, and then the variable name no in brackets. I counted up how many data items I'd got in my list of data, and there were 16 of them. I've given no a value of 16, and then I've said I want C to be a table, an array, with 16 items in it. And they'll be called C1, C2, C3, up to 16. Now, declaring an array to hold numbers is quite straightforward. In line 2, we're defining two arrays, but because the names have $signs in them, it means they're going to hold character values. Again, I've used number here, which has the value 16. And I'm saying I want $F to be an array of character variables, 16 of them. But because it's a character variable, I specify a length here. I want 16 variables, each of which is going to be 13 characters long. $G isn't really an array at all, because I've only asked for one element, but for that element to be 13 characters long. And you'll see why I want $G in just a moment. So our next problem is to take all the data in these data statements and put that data into the arrays we've defined. And that's what happens here. A for next loop. For and next always go together, and they bracket any statements between them and ask them to be repeated. I've said for n equals 1 to no. No has the value of 16, so that's like saying for n equals 1 to 16. I'm saying to BASIC, go around these statements 16 times. The first time you go around, make n equal to 1. The next time, make n equal to 2. The next time, n should be 3. All the way up to this final value, 16. So this read statement is going to be executed 16 times. Now, what are we reading? Well, we have $F followed by n in brackets, and C followed by n in brackets. Like those list of values you saw a moment ago, each of these arrays has all the items in it numbered. Now, the first time I execute this statement, n has a value of 1. So that's like saying read $F number 1 and C number 1. So the first word here, avocado, will be put into the first item in this array $F. The number here, 25, will be put into the first item of C. When we come round the second time, n will be 2, so this will be $F number 2 and C number 2. We'll read bacon and 130. So those two values will go into the second item of each of these two tables. So by the time we've been round here 16 times, we'll have read 16 different foodstuffs and 16 different numbers that go with them. And they'll have been put into the 16 items in $F and the 16 items in C. Now, we only do that once at the beginning of the program, because here's the main part of the program, which is very similar to the part you saw before. The same prompt, enter a food. At this time, I'm using $G number 1. $G was an array with only one item in it. Having input a value into $G, I now have another for next loop. For n equals 1 to no, same as before, n will go from 1 to 16. Each time I go round this set of statements, I make this test. If $G number 1, that's the value we typed in, is equal to $F number n. N is going to be 1 the first time, 2 the second time, 3 the third time. So $G will be compared with each of these in turn, down the list. As soon as we find one that's equal, we'll go to 40. For each one that's not equal, we won't go to 40, We come to the next, and we go round again to try a different value of n. So when we do find that the value we've typed in matches one of these, we come down here to statement 40. We print out the value we typed in, the word is, and then we print Cn. We're going to print the number, the same table number, or subscript as it's called, as the name that matched. So if $1 was equal to F number 5, n will be 5, n will still be 5 here, and so we'll print out the 5th calorific value, the one that corresponds. So these two arrays with the same number of elements in each are held together. As soon as we find a match for one name, we can print out the number that corresponds with it. So what happens here? If we go round and round this loop 16 times and we don't find any sort of match, we'll come to statement number 37. Here we just print out a message saying that foodstuff is not known, and we go back to statement number 10 to try again. So the one final point I wanted to make about this listing is the reason that we used $, being defined as an array, instead of a simple character variable. The reason lies here, in the definition of F$. When we define a character array, we give the length of each string, and those strings are fixed in length. Every item in that array, F$, is 13 characters long. Even if we only put a short word like egg into it, it'll be the 3 letters of egg followed by 10 spaces. So when we do the comparison down here, we need to compare two things of the same length. We know that F$ is going to be 13 characters long, so we want to make sure that G$ also is 13 characters long. And the easiest way to do that is to define it as an array with one element of length 13. You'll find arrays and subscripts very useful whenever your programs contain a lot of information that's basically in the same sort of form. In our example, we had a list of names of foods and we had a list of calorific values. So they were good candidates for putting in arrays. And arrays can also help to speed up your processing, because you can put a large amount of data under one variable name and then pick out individual items of data by using different subscript values. Well, we'll record that program onto the soundtrack so that you can experiment with it yourself and see how we've used the arrays and the subscripts that go with them. And after that, we'll look at some string manipulation. Now, we've dealt with strings of characters in the past, putting values into character variables and getting them out again. But what's very useful sometimes is to be able to take a value in a character variable and extract parts of it, perhaps the first few characters, or the last few, or some out of the middle, to take a substring or a slice of a character string. Well, the Spectrum allows us to do this very easily with its string slicing facilities. And I've got a small program here which will demonstrate that to you. I've started here by putting a value into $, which is just a single character constant. And then into B, C, D, and E character variables, I'm putting various parts of my variable $. Now these brackets after the name $, show which part of the string is to be assigned across. Let's take them one at a time. $3 to 5. That says put into $B that part of the value of $, starting in position 3 and finishing in position 5. So that's C, D, and E. If I miss out the first number, as I have done in the second example, that implies from the beginning, or number 1. So into C dollar, I get from the beginning of $, for the first 10 characters. Similarly, with D dollar, I've missed out the second number here. So that means put into D dollar that part of $, starting in the 6th character, but going on to the end. So that will give me F through to N. And if I just put a single number here, $E equals $3, that means just take one character from $, the 3rd character in this case, the C, and put it into this variable. Well, let's run the program and make sure that it works. That's the series of values that are printed. I'll list the program again so that we can compare. Print $, that's the complete string. B$ should be the 3rd to 5th characters, C through to E, which it is. C$ from the beginning to the 10th character, that's A through to J. D$ from the 6th character to the end, that's the F through to the N. And then E$, the single character in position 3, the letter C. Remember, the quotation marks in the print statement are a nice easy way to get different things printed on successive lines. So we can take a single string and chop it up into separate pieces using the string slicing notation. But it's also useful to be able to join strings together. And we do that with a plus sign. I've extended that coding to give you some examples of that. Now in line 80, I'm putting into F$ the value of B$ plus B$. Well, B$ has been left with the value CDE from this statement, so we've got CDE plus CDE. Basic will make a 6-character string out of those 2 3-character strings and put it into F$. And we can use constant values as well. Here I've taken the constant ABC and added B$ to it. And we can even use string slices added together to make a new string. Here I'm putting into H$, the first 3 characters of $, and the last 3 from 12 to the end. Let's just run that coding to make sure it does work. And you can see I have 2 copies of the string B, CDE, CDE. I have my constant ABC, followed by CDE from B. And I have ABC, LMN, as I expected, the first 3 and the last 3 characters of $. So what sort of use can we put this string manipulation to? Well, word games would be an obvious example. And I've got a program here to play Hangman, which uses some of the techniques I've just been showing you. Well, we've been given a row of dashes, 6 of them, telling us that our word is 6 letters long, and we're invited to guess a letter. Let's try an E. Yes, we have 2 E's in the word. Let's try a G. No, we've started to draw the gallows. An R? Yes. How about a Q? No. A W? A U? An I. There goes the head. An F? An H? No. A T. Oh, we're dead, and we're given the word to show us where we went wrong. So obviously this program needs to look at the individual characters within Word. It needs to take the characters that we type in and check along the word to see if they're present. If they are present, it needs to be able to print them out in the right place in that row of dashes. Now we won't have time to go through the complete coding of this program because it's quite a long one, and we'll record it onto the soundtrack of this video cassette after this session. So we'll concentrate on those statements that deal with string manipulation within the program. Well, this is quite a large program, and so I divided it up into subroutines. 5 main subroutines: to pick a word, to print the row of dashes indicating its letters, to get the one character at a time, which is the guess, to check to see if it's correct, and then the subroutine to do the drawing. Now the first subroutine is the one that picks the word, and that starts in line 1000. I've only got 10 words in the program at the moment, though you of course could change it, and if you do put more words in, then you'll have to change this number. And this statement chooses which word we're going to use this time, using the RND function and multiplying it by the maximum number of words. The restore statement makes sure that the data list will be read from the beginning, and the words in the program are held from line 9000 onwards. So we loop around reading words from our list until we come to the selected word. Now this is the first new facility that you see. A variable called len is being set to the value of the function len. We've put the value $W here, which is the word we chose. This takes the length of $W and puts it into the variable len. So if $W was a 10-letter word, then len would have the value 10. And of course we'll need that value for printing out the dashes, and also for checking each letter along the word. Moving down to the next subroutine, the one starting at line 2000, you see that we use that value, the number of letters in the word, to control this for next loop. That's the one that prints out the dashes, one for each letter of the word. So if it was a 10-letter word, len would be 10, we'd go around this loop 10 times and print 10 dashes. Number of right guesses so far, 0, and the number of wrong guesses, also 0. Now the subroutine at line 3000 is the one that accepts the guess. There's the prompt, guess a letter, and then press enter. And the value we enter goes into $. Because we'll only accept a single letter at a time, we have this test. If the length of $, is greater than 1, then go to 3000. So if we typed in several letters before pressing enter, this statement would make sure we went back, gave the prompt again to try to get a single letter only. It's a very short subroutine because there's the return statement. Here's the next subroutine starting in line 4000. And this is the one that does the work of checking the individual characters. Here's a for loop starting here and finishing here. And n is going from 1 to the length of the word. This test, using string slicing, compares our guess in $, with the characters of $W one at a time. So the first time around, n will be 1, it will be 1 here, and so we're comparing $, against the first character of $W. Second time we go around the loop, n is 2, it'll be 2 here, so we compare $, with the second character of $W. If they're not equal, then we go to line 4050, which is the end of the for loop. If they are equal, we've had a right guess. We score a right guess, and we set that character in $W to to blank to make sure that we don't find it again. So in this case, we're using string slicing to give us the value of a character, but in this case, we're using string slicing to put a value into the character. Here, we reprint $, and the correct point in that row of dashes. So the character we've guessed will go in the nth position, position n, in that row of dashes, because that's the position we found it in. And here, from line 9000 onwards, is the list of words that I've put into the program. Now, I've only put 10 there. When you copy this program into your own machine to see how it works, then you, of course, can add as many more words as you want, or remove some of these. But if you do add further words, don't forget to change the maximum number at the beginning of the program. Well, as I said, that Hangman program is recorded on the videotape immediately after this. And as well as adding your own words to it, you might care to add some extra features, improve the drawing perhaps, or put in a hint facility whereby you can give the player an extra letter or two. So I'll leave that one in your hands. After the recording of the program, we'll look at some animated graphics and the first step on the way to complicated games. Well, this is going to be the most complicated and certainly the largest program that we've looked at during this videotape. And it's going to show us a lot of new facilities of BASIC and some new ways of using the facilities that we already know. So what we'll do, we'll take the program apart piece by piece. We'll look to see what we need to be able to do, and then we'll see how to do it in BASIC. Let's go back to the very first screen. Well, the first thing we see is blocks of color being filled in on the screen, so that the light blue represents corridors in an office block, and the green represents the offices. Here we have the tea lady with her trolley careering around the screen. And notice that we're not doing anything with the keyboard to make this happen. That tea trolley is traveling completely by itself. Here's the little man, and we do have control over him. And we're going to move him by using the keyboard. As you can see, I'm using the 7 key, the one with the up arrow, to get him out, and the 8 takes him left, and the 5 takes him right. That's assuming that we get away in time. Well, we have several different features that we'll need to look at in this program. And we'll start by seeing how we defined those special characters, the little man and the trolley. And in fact, there are some others in the program that you haven't seen yet. We do it like this. Now, this is the section of the program where we've defined the shape for our little man. And if you look very carefully in this block of 1s and 0s, you may be able to see his outline. You'll probably see it more clearly if I color it in a little. Now, wherever I have 1s in that block, that means ink color. And wherever I have 0s, that means paper color. Now, there are other ways to define characters, but this is the most straightforward way. we have 8 data statements here, and they're using bin. That stands for binary, saying that the data in this statement is going to be in binary format. Now, if you don't understand binary, if you haven't used it before, then don't worry, because as long as you follow the principle of defining an 8 by 8 block of ones and zeros, and making sure that your shape is outlined by the ones in that block, then it's going to work. So let's describe the shape. Now, how do we tell the spectrum that that shape represents one of our characters? Well, we use coding like these 4 statements. The for loop, and here n is going from 0 to 7. So 8 times, that's from 0 to 7, we're going to read a variable m, and we're reading these binary values from these data statements. The poke statement is used to put a value directly into the memory of the computer. That's the value we're going to poke in, which is this series of binary numbers. And that is the place we're going to poke it. If I say user, followed by a letter, in quotation marks, in brackets, then the spectrum knows that I'm going to define a special character, define my own shape of character. Now, in the manual, you'll see examples of this coding, and the easiest thing to do is to copy that exactly when you define your own characters. Now, we can define our characters using letters from A up to U. I used M here to remind me that it was the man. For the trolley that went around the screen, I used user T and a different set of ones and zeros. But the principle is exactly the same, and you can copy coding like this into any of your programs when you need to define a special character. Well, having defined it, we next need to know how we use it. And we use it in a print statement like any other character. Well, here's a print statement that prints one of our special characters, the little man. And it appears within quotation marks just like any other character. But of course it doesn't appear on the keyboard, so how do we get it printed? Well, I'll enter another print statement, and you'll see how we achieve it. Print, and a quotation mark. Now, we defined our little man as graphics character M. And to get that into our print statement, we have to hold down the caps shift and press the 9 key, which has graphics written above it. Now you see that our cursor has changed to a flashing G, and this means that we're in graphics mode. If we now type a letter between A and U, we won't get the letter, we'll get a graphics character that we've defined for that letter. If I now type M, I don't get the letter M, I get my little man. Notice that I still have the flashing G as a cursor. Once I've gone into graphics mode, I will stay in graphics mode as I continue typing. Now that's not like extended mode, which reverts to normal as soon as I've hit another key. So in order to get out of graphics mode, again I hold down caps shift and press 9. You can see now I have my flashing L cursor back. I can now put my closing quotation mark, and there's my print statement containing one of my user-defined characters. So user-defined characters give us an alternative way of building up an image on the screen. We could use plot and draw and circle and build up line drawings that way. But when we have shapes, especially ones that need to be repeated and moved around, it's often a lot simpler to define our own special characters and use the graphics facilities that we just saw. Now, another thing about this program that's very different to ones we've seen before was the fact that we were able to enter information into the computer just by pressing keys without pressing enter after every one. Now, this obviously means we weren't using an input statement, we were using another facility. But if you look at this part of the program, you'll see how we did it. Here at the beginning of the program, you can see the main logic. It's a loop that goes from line 100 here, round to line 800 here. And most of the work is done by calls to subroutines. Go sub 1500, go sub 2500, go sub 2000, go sub 3000. Each of those subroutines performing one specific task. Which one of them we call depends on this value of $A. W, 4, 9, P. And this statement in line 100 is one that sets the value for $A. Now I'm using a function called InKeyDollar, and that's the one that does the input. The value that InKeyDollar gives us is the single character corresponding to the key that was being pressed at that particular moment. So when line 100 is executed, if one key is being pressed at that moment, then the character corresponding to that key will be put in $A. If I don't have my hand anywhere near the keyboard, then $A is set to a null string, a string of length 0. So we can still be ready to accept input as we go round and round here, but we're not stuck waiting for the enter key to be pressed. Because although most of these lines act on the result of comparing $A with another character, there's one particular line, line 130, which is always executed, go sub 2000. And it's the subroutine at line 2000 that controls the T-trolley. Remember, the T-trolley continues to move around even when we're not pressing any keys. So because InKeyDollar doesn't wait for a key to be pressed, the program is continually looping around here. And every time it goes around, we have a chance to move the T-trolley, whether we're moving our man or not. Now, if we watch the T-trolley as it charges around the screen, you'll notice that it stops each time it hits a wall, and then goes off in a different direction, choosing randomly whether it goes back or turns to left or right. But the important thing is to be able to detect that it has reached a wall, and that it doesn't go straight through the wall, through to the other side. The same applies to our little man. If we take our little man out, and we try to run him through the wall, he stops. The program won't let him go through the wall. In fact, there are two different types of collision detection that we need to have in our program. Now, the one kind is when the T-trolley or the man comes up against a wall, because the walls are large objects, they fill a large proportion of the screen, and so it would be very difficult to test to see if each part of the screen was wall or not wall. That sort of collision we detect by looking at the color. Now, the other sort of collision is when the man and the T-trolley itself collide. And the way we handle that is by comparing the coordinates. We have variables in our program which tell us where the man is and where the T-trolley is. We can compare those coordinates. If the coordinates are the same, the man and the T-trolley are in the same place, and so we know that they've collided. Let's look at the coding we use to solve these problems. Now, the subroutine at line 2500 is the one that moves the man around. The first thing we do is to print a space in the man's position. X and Y are the variables used to keep track of the man's position. And because the man is being displayed as a character, then those are character positions and not graphics positions. 5, 6, 7, and 8 are the keys we use to move him left, right, up, and down. So these statements simply decide in which direction we want to move him. These statements change X and Y according to the direction in which the man is moving. Now we have two tests for collisions here. This first one tests to see that the man isn't trying to go off the screen. If x became less than 0, or y became less than 0, it would mean that the man was trying to go off the screen to the left or off the screen at the top. X being greater than 31 or y being greater than 21 are the other two sides of the screen. So if any of those are true, we can't let the man move. So the OR between these tests allows us to combine all the tests together into one big test. Now this next line uses the function point to test to see if the man has come up against a wall. Now this rather complicated expression is needed because x and y are character coordinates. The point function tells us the color of one point on the screen, one graphics point. So these two calculations convert between character coordinates and graphics coordinates. If that particular point on the screen is paper color, we get a 0 as a result. If that particular point on the screen is ink color, we get a 1. So within our program, we can look at any point on the screen and decide whether it's been painted in ink color or paper color. Now the green blocks were in ink color and the blue corridors are in paper color. So we can make the decision as to whether we let the man move or whether we prevent him from moving. There's our print statement, which will print him in the new position if he has moved, or we'll put him back in his old position if he hasn't moved. Now we can see an example of the other sort of collision detection in the T-Lady subroutine. Here, in statement 2031, Tx and Ty are the x and y positions of the T-Lady. X and y are the x and y positions of our little man. So if the T-Lady's x position is the same as our man's x position, and the T-Lady's y position is the same as our man's y position, then they're in the same place. If they are in the same place, then we call the subroutine at 6000, which is the one that produces the message saying that we've been splatted. Well, there's another obvious change that we've made to the program now, and if you listen carefully, you'll hear it. It doesn't sound quite like chinking cups, but it gives a fair approximation. Well, here's the statement that made that noise. Line 2120, a beep statement. We put two numbers after the beep. The first number is the duration of the sound in seconds. As you can see, that's a very small time. The other number is the frequency of the sound. If that was 0, it would be around middle C. Numbers greater than 0 go higher, and numbers smaller than 0 go lower. One of the reasons I made this such a small time, such a short duration, is because while the computer is making your beeping noise, it can't do anything else. So if you ask for a long beep, that's going to slow down the program quite considerably. So if you want to use beeps in your program, it's better to use short ones than long ones. Well, we haven't had time to tell you all the features of this game. We haven't shown you the bucket of water to drop on the bomb. Oh, we didn't tell you there was a bomb to find. And you've got the problem of escaping before the bomb explodes. And that area on the left is a pointer, which is going to tell you how far you are from the bomb and in which direction it is. That's assuming you get close enough to drop your water on the bomb before it goes off, and assuming that the T-Lady doesn't get you first. Well, we've come to the end of this videotape. we've shown you quite a few basic statements and facilities and some techniques for using them. But really there's no alternative but to sit down with your own computer and practice them. You'll need to spend quite a long time looking at the manual, checking statements, and looking at the examples of coding that you'll find in there. And I hope that you'll find the coding that we've recorded on the soundtrack for you to copy into your own computer. We hope that that'll be useful as well. Don't expect that you're going to learn BASIC immediately. It does take quite a lot of practice before you can become completely fluent, so that you know your machine, you know your keyboard, and you know what statements do what. But given time and a little bit of application, I'm sure you'll get as much fun out of writing BASIC programs as I do.